Today we are here at the Columbus Curling Club to uncover the secret behind how curling works. Now, unless you are either Swedish or Canadian, you probably don't know what curling is. So let me explain. Curling is an ice sport played on specially prepared ice. There are 4 people on each of 2 teams. They fight to the death to end closest to the middle of rings. After all 16 stones have been thrown, the team that is closest to the middle scores 1 point for each stone that is closer to the middle than the other team.
Teams take turns throwing stones down the ice. This involves balance and aim, as a stone thrown improperly may miss its target. This is much more difficult than it looks, as Teran, a first-time curler, shows when he tries to keep upright sliding down the ice. This is vastly different than a veteran curler such as John, who maintains balance as he throws his stone. After the stone is let go, team members join in by using specialty brooms that are swept across the ice to change the speed and direction of the traveling stone. They may not touch the stone with the brooms. This sweeping process is what makes the physics of curling complicated.
Now, you may think that sweeping the ice makes the stone curl more. However, this is not the case at all. Actually, sweeping the ice creates a thin layer of wire, reducing friction and allowing the stone to travel faster and further. You can actually see the difference here when a stone is thrown with no sweeping, followed by one that is swept. This is a section of ice that has been untouched by a broom. You can see that it is smooth and relatively free of cracks. This is a section of ice that has been swept with a broom. You can clearly see the grains that were formed by the liquid wire created when the broom heated the ice. This then froze and formed the structure seen here. Physics go much deeper than this. There are 2 current theories on how the stone interacts with the ice in regards to the coefficient of friction. The first thesis is called the scratch theory. It involves the scratches that result from what is called the running band of the stone. The running band is a circular section of the stone that touches the ice. As it moves across the ice, the running band makes scratch patterns that resemble sine and cosine curves. Scientists believe that because the rough spots at the back of the running band have to grind over those already created by the front, this creates a downward force that causes the stone to curl in the direction of rotation. The other major thesis is called asymmetric friction melting. This is believed to be the product of the running band melting the ice as it travels down the ice. In this theory, the ice at the front of the stone generates more friction than at the back, as the stone is constantly trying to flip over as it moves forward. This is then expanded to show that the side of the rock that is advancing faster is therefore generating more friction and melting more ice. This liquid wire then makes its way to the leading edge of the stone, allowing it to accelerate more in that direction. These 2 effects combine to push the rock in the direction of rotation.
Collisions, the most exciting part of any sporting event, be it big hits in football or hockey, to multi-car pileups in NASCAR or Formula One, are also present in curling and allow for some of the most technical power shots seen in any sport. The collisions in curling are almost perfectly elastic, meaning that they lose very little kinetic energy in the collision. This is thanks to the special type of Scottish granite which the curling stones are made of. The granite is found to be more durable and a better conduit for the energy than granite from any other location in the world. When the stones collide, the initial stone, moving with some velocity and a mass around 42 pounds, collides with another stone that was at rest and has the equivalent mass. Suppose there are 2 stones, stone A, initially moving, and stone B, initially at rest. Depending on the angle at which the initial stone hit, one of 2 things happen. If stone A hits stone B directly at the center, stone A stops at the point of the collision and transfers almost all of its momentum over to stone B, which will then travel with a velocity close but less than the initial velocity. If stone A hits stone B at an angle off-center, then stone A transfers some of its momentum over to stone B. Because of the angle, stone A retains some of the momentum and continues moving. Stone B will also begin to move, but both stones will move with a velocity much less than the initial velocity of stone A. This transfer of energy is directly proportional to the angle of the collision. Now, you will see a couple of other examples of collisions in curling.
Let's recap what we've been over today. First, we looked at how curling is played by visiting the Columbus Curling Club. There we saw examples of how not to and how to throw a stone. Next, we explored how sweeping changes the coefficient of friction ahead of the ice to control how far the stone will travel. Then we saw the two competing theories of why curling stones tend to move in the direction that they are spun and the underlying physics that powers them. The first one states that it is because of the scratches created by the stone on the ice. The second claims that it's because of the difference in the melting on the front versus the back of the stone. Finally, we looked at how momentum dictates the physics of the stone-to-stone interactions by studying head-on and side impacts of the stones. As we have seen, the physics of curling are far from boring. Although curling may seem like a simple sport at its surface, however, the physics are far too large to just be swept under the rug.